Okay.
Okay, so good afternoon, teacher and friends. Today I will be presenting about organic chemistry. So first, we have to know why is it called organic chemistry? It's because we believe that the chemicals or compounds here are mostly formed from organisms, hence they're called organic. So next, I will be covering these topics. We will start off with naming organic compounds. So how do we name organic compounds? First, you have to find the suffix, which depends on its functional group. So let's say if my functional group is alkane, then my suffix or ending will end with ane, ane. And second, you have to find the prefix. So it depends on the number of carbon atoms. For example, if I have 6 carbon atoms, that means my prefix will be hex. And then if I have hex, 6 carbon atoms, and then it's an alkane, then it's hexane, hexane. Then the third one is you have to determine the position of the functional group. So here I have the example. Because there are 4 carbon atoms, you can call it bu. And then because they're all single bonds, we can know that this is an alkene, hence it's a butane. And then because there are 2 methyl groups, they're called dimethylbutane. The only difference between these 2 pictures is only the position of the methyl group. So for the left one, since it's on the second and third carbon atom, you can call it 2,3 dimethylbutane. And then for the right one, because both of them are on the second carbon atom, you can call it 2,2 dimethylbutane. Next will be describing organic compounds. So there are 3 ways in which you can describe organic compounds. The first one is through their molecular formula, which is displaying the number of atoms of each element in a compound. So here we'll be taking ethane as an example. So because there are 2 carbon atoms and then we have 6 carbon atoms, it will be C2H6. And then the second one is the structural formula. So it displays the number of atoms of each element in the compound based on the number of carbon atoms. So I can, still using the same example, ethane, I can split C2H6 to CH3 and CH3. And then the next one is displayed formula. So this is the easiest. It is the type of structural formula which shows all of the covalent bonds. Next, we have homologous series. So what exactly is homologous series? It's a series or family of organic compounds that have similar features and chemical properties due to them having the same functional groups. So their first characteristic is that all members of the same series have the same general formula. So let's take alkane as an example. Alkane is a functional group. So all the members of alkanes, like methane, decane, hexane, they will all have the same general formula, which is CnH2n plus 2. And then the second characteristic is that all members of the same series have similar chemical property. And then third one is that their physical properties differ in a predictable manner. So for example, methane and ethane are gas. Then propane is also gas, but it can be compressed to liquid. Pentane is a volatile liquid, and then octadecane, C18H30 is a solid. So as you add the number of carbon atoms, you can see the difference in the state of matter, and then it's predictable. And then the last one is consecutive numbers differ by CH2. What I mean by this is that, for example, methane is CH4, and then ethane is C2H6. So they differ by 1 carbon atom and 2 hydrogen atoms. Next one is alkanes. So what are alkanes? They are saturated hydrocarbons and they're called saturated because they only have single bonds. And then their general formula, as I mentioned before, is CnH2n plus 2. And then they end with the prefix ane. So they can undergo 2 types of reactions. The first one is combustion. Combustion is basically the burning of chemicals in the air or exposure to oxygen. And there are 2 types of combustion. First one would be complete, where there is sufficient oxygen in the air. So these types of reaction will always produce carbon dioxide and water. But then the other type is incomplete combustion, which means that there's an insufficient amount of oxygen in the air, leading to the formation of carbon monoxide. And then the other reaction would be substitution. This relates to free radical chlorines, and uh, if enough, oh, sorry, I mean the chlorine atoms, they replace the hydrogen atoms. So they substitute the hydrogen atoms, hence the name substitution. And if enough chlorine is present, the reaction will go on until all of the hydrogen atoms have been substituted. Next, we have alkenes. So alkenes are unsaturated hydrocarbons, and they're called unsaturated because they have double bonds. And then they have the general formula CnH2n. So the number of hydrogen atoms is twice the number of carbon atoms. And then they end with ene, ene. So there are four types of reactions associated with alkenes. The first one is the addition of bromine, or you can call it halogenation because bromine itself is a type of halogen in the periodic table. And usually this is used as a test to distinguish alkenes and alkanes because in the presence of alkenes, the brown color of bromine will be discolorized, so it turns colorless. And then the reaction is available on the slide. And then the next one, we have addition of hydrogen, and the name itself is hydrogenation. So it's literally like that. And then the conditions required are temperatures of 150 degrees Celsius and then a catalyst of nickel or platinum. And the reaction is written on the slide again. You can read it yourself. And then for the addition of water, again, it's hydration because it relates with water. And then the requirements are temperatures of 300 degrees Celsius, pressure of 60 atmospheric pressure, and the catalyst phosphoric acid. And then the next one is addition polymerization, which I will explain later on. So these are alcohols, carboxylic acid, and esters. First, we will look at alcohols. So alcohols, they have the general formula CnH2n plus 1 OH, and they have the suffix OL, so they end with OL. And then they can be made from dehydration of alkene or fermentation. So for the reaction of fermentation, I put it as glucose fermented to ethanol and CO2. And there are advantages of hydration and fermentation. So for hydration, it's renewable and they require less energy. But then the disadvantage will be that it is a slow process and it produces CO2. And then the advantage is no waste products. There's a rapid production of ethanol with fermentation. And then the disadvantage will be it uses non-renewable crude oil and requires lots of energy for high heat and pressure. Then the next one, we have carboxylic acid. So all carboxylic acids are weak acids. So you have to know that weak acids always ionize partially in aqueous solutions. And then they have the general formula CnH2n plus 1, COOH. And then they end with boric acid, and they can be made by the oxidation via fermentation or oxidation with acidified potassium manganate. And next, we have ester, which is a product of carboxylic acid alcohols. Their esters are formed in a process called acidification. So usually carboxylic acid plus water will make ester, carboxylic acid and alcohol will make ester and water. And then we will discuss again in the next slide why the sulfuric acid is needed. And then naming esters, you have to know that the alcohol part comes first, and then the carboxylic acid will come last. So this is a quick recap of how we can turn alkanes to alkenes, alkenes to alcohol, and so on. So please focus on this area, which is alcohol plus carboxylic acid equals to ester. So as I said before, when alcohol reacts with carboxylic acid, not only ester is formed, but water is also formed. So the sulfuric acid here, besides acting as a catalyst, it also acts as a water remover. So the sulfuric acid makes sure that the water is going to be removed. And in case you want to know how cracking works or halogenation occurs, you can ask me later at the end of the presentation. And then Fuels are the example of thermal cracking. So the hydrocarbons in crude oil are heated at high temperatures to break the molecular bonds and breaking down long-chained, higher boiling hydrocarbons into shorter-chained, lower boiling hydrocarbons. There are three main fuels that you have to be familiar with. One is coal, and it is formed by the decay of organisms over millions of years. Second one will be natural gas, which is mainly methane, usually produced by cow farts. And then the last one is petroleum, which is crude oil itself, which is a complex mixture of hydrocarbons. So refinery gas, or usually we call it LPG, it's usually made up of propane or butane, and then they're at 25 degrees Celsius, gasoline at 30 degrees Celsius, naphtha at 110 degrees Celsius, kerosene at 180 degrees Celsius, diesel oil or gas oil at 260, fuel oil at around 300 degrees Celsius, lubricant oil at 340 degrees Celsius, and residues such as bitumens or asphalts at 400 degrees Celsius. So as we go down, we can see that the boiling point increases and then the hydrocarbons become less volatile and then their viscosity increases, which means that they flow less easily because they become thicker and then they also become less flammable. So next we have addition polymerization. So addition polymerization is basically a polymer, the formation of polymer that forms by a simple linking of monomers without formation of side products. So for example, ethene, C2H4. In addition polymerization, the double bond can break into single bonds. So now the carbon has one free arm, which means it can link with one another. So in addition polymerization, the monomers will break their double bonds and then they can spread open and then they line up side to side, forming a long chain. This type of reaction is usually done only for double or triple bonds, so basically unsaturated hydrocarbons. And then to name the polymer, you can add poly to the monomer's name, and then you add brackets to the monomer's name itself. So for example, the polymer of ethene would be poly, bracket open, ethene, bracket close. So you can write it like this. So you can draw the ethene, the monomers, and then the catalyst pressure, and then the polymer. However, the problem associated with this is that sometimes reactions can take up to hundreds of monomers. So instead, you can simplify it like this. So you can put an N and then a bracket, you put your monomer inside the bracket, and then you do the same for the polymers with repeating units. Next one, usually addition polymerization is used to produce natural polymers like protein, starch, cellulose, some things like that. So proteins are built from amino acid monomers that are joined together via the amide link. And this is a reversible reaction, so they can be hydrolyzed back to amino acids by boiling with hydrochloric acid. And then the next one, we have polysaccharides, which are made from many simple sugar units. These polysaccharides can be, an example of it can be starch or cellulose. And this glucose can be hydrolyzed back to simple sugars by heating with dilute HCl. This is the summary for how we can do addition polymerization. So first you have to break the double bonds open so that they can form links with each other. And then they form one long chain known as the polymers. And then you can put them in brackets like how I said earlier. And then next we have condensation polymerization of polyamides or nylon. So condensation polymerization involves monomers with different functional groups. They are characterized by 2N filled with the functional group. So instead of monomers reacting to form a single product like in addition polymerization, in condensation polymerization, polymers are formed along with the release of a small molecule which can be HCl, H2, or water, usually water. And then let's take this as an example. So when two two of them join together, they can form one polymer and then they also release a small water molecule over there, represented by the red ball and two white balls. So here we have an example. Let's just take the black balls as the carbon, the white balls as the hydrogen, the blue ones as amine, and the red ones as carboxylic acid. you can simplify this diagram by replacing the hydrocarbons with a rectangular block to make it simpler. And I'm giving an example of the formation of nylon 6,6. So the one at the top is a molecule of hexane 1,6-diamine. It has amine group on both ends, represented by the blue balls. And then the one at the bottom is hexane dioic acid with carboxylic acid functional groups at both ends, represented by their red balls. Since carbon and hydrogen are the same again, it can be substituted with a rectangular block. And when a carboxylic acid group and amine group is placed next to each other, they react to form water, which is eliminated. And then a large polymer molecule held together by amide link is formed. That's why it is called polyamide. And then nylon have many uses in the textile industry, and they're also used in engineering. Next one, we have the condensation polymerization of polyesters, or PET. So polyesters is an ester which is formed by the reaction of an alcohol and carboxylic acid. PET, or polyethylene terephthalate, is made of benzene 1,4-dicarboxylic acid and ethane 1,2-diol. And the PET is often used for plastic drinking bottles and fabric for clothing. This is the summary of the difference between addition and condensation. So first, addition is only made of one type of monomer, which only has one type of functional group, but then condensation can be made of two types of monomers with different functional groups. And then the second one, addition polymerization, only form one polymer and no side products, but condensation may produce small molecules at side products such as water, hydrogen chloride, or hydrogen gas. And then the third one is that addition polymerization is usually used for the manufacture of synthetic polymers like PVC and polystyrene, but the exception would be rubber latex, which you can usually obtain by tapping the rubber tree. And then for condensation is that usually manufactures natural polymers like proteins, carbohydrates, starch, and then the exception will be nylon, like what I explained earlier. Thank you.
Okay. Is there any question? It was quite very complete. I can say complete organic chemistry. Even Felicia made already the mind map for the organic chemistry. Is there any question? From Bavia? It's okay, Bavia, you can ask question to Felicia.
No questions, teacher.
No question. How about from Ariela?
No questions.
No question. Lawrence?
No questions.
No question. And then if let me ask from Natasha.
No question, teacher.
No question. Okay. First, I would like to ask Felicia some first question. This one about alkanes and alkenes. We know that alkanes can be converted into alkenes, and alkenes can be converted into alkanes.
Yes.
What is the term when alkanes is converted into alkenes?
The process is known as cracking or catalytic cracking.
Yeah, catalytic cracking. What is the catalyst?
The catalyst would be aluminum oxide or zinc oxide or silicon dioxide.
Condition.
The conditions required will be 500 to 600 degrees Celsius.
Yes, correct. When we are talking about cracking, right? Cracking cracking of long chain alkanes will produce three possible products. What are those three possible products?
Usually it's one small alkene, and then two of them will be the alkanes, the remaining alkanes. So in the
One.
breakdown of decane, it will make 18 and octane.
Okay, it is the three products: small chain alkanes, small chain alkenes, and hydrogen gas. You still remember in Haber process there was a source of hydrogen. Source of hydrogen is the cracking of hydrocarbons. Okay, still about alkanes and alkenes. How to differentiate alkanes? How to make them differ? How do we distinguish alkanes from alkenes? What is the simple test?
The simple test would be adding bromine water. So it's a dilute solution of bromine. So in the presence of alkenes, the bromines would turn from brown to colorless, but in the presence of alkanes, it would still remain brown.
Yes, correct. On your slide, this one, on the right hand side, substitution. Substitution, this is a reaction or substitution reaction. What is the catalyst?
It's UV light, so it relates with the depletion of ozone layer.
Why is catalyst used in substitution of alkanes?
Because the chlorines are free radicals. So when the chlorine atoms are exposed to the light, they become chlorine radicals, which can substitute the hydrogen atoms in the hydrocarbons.
Yes, that is the effect after using catalyst. But I asked, why is catalyst used?
So in general, why is catalyst in general used?
Yeah, why is it used? It is in chemistry. We learned already in speed of reaction chapter.
So catalysts are usually used to speed up reactions because they have special active sites. So they make the particles or molecules collide with one another more frequently, so the chances of successful collisions will be higher. And because of these higher chances of successful collisions, that the reaction will be more rapid.
Yeah, it's correct. It is correct, but not complete. Uh, Catalyst is used to lower down the activation energy. Okay, so catalyst is used to decrease the activation energy by finding the alternative pathway. Okay, now next the alkanes, two halogenoalkanes already, and then alkenes into halogenoalkanes. It is called as addition. Am I right? Alkenes to halogenoalkanes is called addition reaction. How about halogenoalkanes become alkenes?
It's known as elimination.
Elimination. Okay, correct. And then alkenes become alcohol. It is called hydration. Alcohol becomes alkenes is called,
Elimination or dehydration.
yes. How to make alcohol become alkenes?
Um, the
What is
requirements
the
are heat, so
catalyst?
160. Oh, the catalyst is concentrated sulfuric acid. So
Yes,
similar to esterification, the sulfuric acid, besides acting as a catalyst itself, it also helps to remove the water.
exactly.
So the alcohol will be dehydrated and then it turns to alkenes.
Yeah, exactly. And then now about carboxylic acid and ester. Carboxylic acid, ester. Uh, is carboxylic acid and do both of them called as isomers?
Um, I don't think so, sir.
You don't think so? Okay. Now, since you this one, can you op- provide a blank paper, uh,
In
blank,
WebEx,
yeah, blank sheet, or that you can draw paint paint program. Now, okay, can you draw the structure of butanoic acid? You have to draw the structural formula of butanoic acid. Yeah. Yes. Yeah. Butanoic acid. Yes. Correct. So in here there are 8 hydrogen atoms. Am I right?
yes.
Now can you draw ethyl ethanoate? Ester ethyl ethanoate. Ethyl ethanoate. Mhm. Yes. Yeah. How many hydrogen atoms are there?
9.
Are you sure?
Oh, there are 8, sorry.
8. So carboxylic acid and ester, they are isomers. They are isomer to each other. Okay. But of course, they have different properties. Now, let me ask about the boiling point. Carboxylic acid has higher boiling point than an ester. Give an explanation.
To why it has higher boiling point than ester.
Yes, general carboxylic acid, the same number of carbon atoms. Carboxylic acid has higher boiling point than ester. What is the reason? If you ever seen on the answer of the IGCSE mark scheme, you will find the abbreviation VDW. Do you know what does it stand for?
Van der Waals.
Exactly. So IGCSE is using this term. So it means that when you answer the question of IGCSE, you can include van der Waals, also hydrogen bonding, permanent dipole, and also temporary dipole-dipole forces. Now, can you tell what is the reason that carboxylic acid has higher boiling and melting point than an ester?
Carboxylic acid has stronger van der Waals forces between them, so higher energy is required to overcome the bonds.
No, it does not have van der Waals. It has hydrogen bonding. Carboxylic acid has hydrogen bonding. Ester has van der Waals. So hydrogen bonding has is the strongest intermolecular forces compared to van der Waals. So what they want to see, they usually give this one to marks. And then now I would like to ask, is are my questions difficult, Felicia? No, right?
I wouldn't say it's easy, teacher.
Okay, let me okay let me ask from last time. Okay, thank you for the presentation, Felicia.
Thank
Let
you,
me
teacher.
ask Carlton. Hello, Carlton. Can you tell me what is the topic of your presentation? And then Mario, you have to make presentation also. You have not told me what is the title of your presentation. Okay, now let's go back to Felicia again because there is question about organic chemistry. Okay, organic chemistry, Felicia, can is it possible that you draw all the isomers of C4H8?
Butene.
Yes, C4H8. I did not say butene. C4H8.
Teacher, why did you give hard questions?
Yeah,
Yeah.
because this isomer last time the IGCSE student could not answer this question. They had difficulty. Oh, Felicia, maybe you can draw CH3, CH2. So
Okay.
no need to make the structure because it will take longer time. I'm sure all your friends know already what does it mean by CH3.
This one will be but one because double bond is present on the first
Yeah, and
and
then
and then for the second one, for butene, the double bond will be right here. So on the second carbon atom, and then this
yes,
will be single bond,
yes.
and then
How many isomers would there be for C4H8?
uh, four to five.
4 to 5. Okay, can you draw all the isomers?
Oh, this one's wrong.
Yeah, there are 5 isomers.
This one would be called
This
because it has a methyl group on the second carbon atom. It will be called
methyl propene
methyl methyl to propene.
to methyl propene. Okay.
Oh, to methyl.
And what is the fourth isomer?